Hi, I'm Dan Fritchman from UC Berkeley, and I'm happy to be here today to present our framework for programming circuits and layouts called VLSIR. First, a bit about me. I started my career as an embedded system designer, and I've spent the bulk of it designing analog and mixed signal circuits for digital SoCs, a lot of the time at Apple. The last few years, I've been a PhD candidate here at Berkeley, focused on the software behind our field, particularly analog and mixed signal circuits. And I frame the problem facing us as we've essentially established two successful ways to produce IC layout in the history of this field. You could call them the digital way and the analog way. At left, the former, in which designers dictate HDL code and some set of physical constraints into a sort of compiler pipeline that produces physical layout. And in the latter, the analog mode, the designers really manipulate the final output very directly, generally in GUI form. Now, there have been plenty of recent research efforts, including at our own institution, to find sort of a third way, and particularly to improve upon the one at right, which commonly forms a bottleneck. Some of those projects include Align, Magical, and your Berkeley BAG. And none have really gained much of a foothold in terms of changing the culture or changing adoption amongst designers out there in the world to generate the kind of productivity gains that we would want to get, the ones that our digital colleagues long since enjoyed. We have some theories as to why, and they do require some ground up rethinks of some important subcomponents in the VLSIR project. And the first is the design data itself. So VLSIR is centrally built upon a design database defined in Google's protocol buffers format. That is an efficient binary data format that is strongly typed through a dedicated schema description language. A compiler then turns such data schemas into binding code for essentially any popular programming language, allowing us to write programs manipulating its content in each of those languages, making different trade-offs between performance, accessibility, ease of use, and the like. VLSIR defines such schemas for circuits, for layout, and for simulation input and output, and includes, or its family includes, a variety of user interface front ends for generally per each of those tasks, and a series of backends that typically do things like interact with the industry standard tools, formats, and the like, such as GDS, LEF, popular spice engines. And one of the types of things in those design databases I will introduce a little bit roundaboutly by trying to pretend to describe it to someone outside our field. And I use this I call this hypothetical a dinner party test, in which we're going to try to explain one of these things to someone smart, but not a specialist, maybe someone in law or medicine. As a few examples of what I think are easy examples of this. First, sort of what is this? I think is quite explainable. It's sort of a list of instructions for a computer to execute top to bottom. There's some specialty ones that redirect program flow, but by and large, it's sort of a recipe for what the computer is to do. Number two, I would describe as a physical blueprint, right? So this is an IC layout. This is essentially a 2.5 dimensional physical picture in which the colors are sort of z-axis indicators in and out of the monitor, and X and Y indicate spatial coordinates in those dimensions. Now, the third such test is the hard one. And while I noted I'm an analog designer by trade, I don't on some level know the answer to what this is. Clearly, this is an op-amp, this is a schematic, but why these pictures and these squiggly lines have such intuitive control over my and many other in the field's understanding of these circuits, on some level, I can't explain. Now, these have been the lingua franca for the field essentially forever, certainly throughout my time within it. And this is true for the best of schematics, the sort of most evocative of what they do. Now, for those who've been out in the field, you see most real schematics tend to look more like so. with two giant rectangles and 500 connections in between them. Most signals have several underscores, essentially making informal hierarchical references. This is not a great way of describing, documenting, or really doing very much with very complicated things. The one thesis of the VLSIR system is most of these schematics would be much better served as pieces of code. The primary piece of software that we use to do that is called HCL21. That is a hardware description library embedded in Python. Its central intent is exposing the idea of programming these analog circuits to designers who know how to make them. And an important fact about those designers is they're often not super skilled programmers. So we expose the concepts that they are used to, such as modules and signals and ports and instances of other subcircuits, in the most accessible mode that we can. Now, while the most common means of defining HCL21's core reuse element, which is called module, shown here via Python class, it also extends downward to for designers who can write at kind of script level and just manipulate variables directly without any class or data structure and concepts. Now, the power is, of course, really enhanced using the more advanced features, particularly the HCL21 generator facility. HCL21's generators are functions that produce modules and are free to do so via any algorithmic, any code-based means that they like. Those two ideas really are the central concepts to making powerful parametric hardware. Now, HCL21 also includes all of the things that a practitioner in the fields uniquely knows and loves and needs, such as PVT corners, drivers for popular SPICE simulation engines, primitive elements such as passives, transistors, and the like. And it also includes many that most practitioners would swear up and down they don't need or use, but actually do use all the time. Some prominent examples are things like structured connections. So this is the concept that System Verilog calls interface, Chisel calls bundle. HCL21 also calls bundle. These are sets of signals that travel together. You can almost certainly think of many such examples. An especially prominent one in analog circuits is differential pairs, which is called diff. That one is so special that it is built in and in fact includes built-in facilities for doing things like connecting differential instances of hardware to it in the pair constructed bottom right. So hopefully it's clear. I think most schematics should probably be replaced by pieces of code, but there really are some that continue to convey some very valuable information graphically. And HCL21 as such attempts to get the good without the bad. By getting these in and out of code as fast as we can. The HCL21 schematic system does so by making each schematic a standalone SVG image, which is also essentially executable as a Python module. It runs as an HCL21 generator. One very helpful fact about making schematics out of general purpose image formats is that platforms like GitHub and GitLab can render them directly. There's no setup, there's no linked database or anything to render these images on those sites. The primary means of editing and interacting with HCL20 schematics is also designed to get them in and out of code as quickly as possible, which is that it's a plugin, it's an extension for the most popular IDE, Microsoft's VS Code. The file pulled from the panel at left, inverter.sch.svg, given an extension to that editor, opens in graphical mode with full GUI editing support. The Python file at left, making a ring oscillator out of that inverter, imports it directly as though it was any other chunk of Python code. Now, referring back to our initial premise about how IC circuits get designed, we get to VLSIR's handling of layout, which is to say it is diverse. So VLSIR is designed to be modular and to not force all-in-one adoption. And it also is designed to be layered and targeted for different applications at different times. There have been two categories of attempts at improving this analog design flow at Wright among the recent research works. Align, Magical, and others do something like applying the paradigm at left, the digital place and route compiler, to analog circuits, requiring a more elaborate set of constraints and dictations from the designer. BAG, in contrast, essentially does what I call programmed custom layout, in which all of the GUI manipulations at right are essentially replaced by API calls to add shapes, add instances of other layouts, run simulations, and the like. The VLSI system is designed to support both. We spend a lot of our time on the right category of programmed custom, and there is a chunk of the framework dedicated to both raw layout manipulation. This all falls under a project called Layout 21. So in the former, one can manipulate IC layout programmatically at as granular of a level as one wants. The slightly higher level exposes called Tetris, which operates on a rectilinear grid and predefined or shared tracks. Routing in Tetris is, as in most such systems, the most delicate and complicated element. And its premise is that routes are essentially programmed signals onto intersections between tracks and adjacent layers. So essentially signals programmed to vias is the routing method, coupled with cutting tracks as an API. Now, while that serves for the programmed custom layout method, VLSI system is also designed to support analog PNR and compilation, and is in some senses better suited to do so than the digital pipeline itself. So we note that in the typical digital flow, there really are two designer inputs, and in fact, there are often two different subspecialties of designers producing them. One is HDL code, generally at RTL level, to describe the circuit, and two is some physical information describing constraints about what size and shape it should take on, clock frequencies, what are goals for what the PNR compilation stack should do. In analog circuits, those things are often more intertwined, and having an HDL, a hardware description, embedded in a general purpose programming language proves a very valuable place to intertwine them. HDL21 serves as essentially the hub of all of such information. So it certainly includes, in what you've seen in prior slides, include everything that would go into a typical IC netlist, but also it includes a home for all of the sort of constraint destined information, such as which signals and instances are differential or must be matched, relative importances thereof that feed into the constraint input of a typical such PNR program. So we have been developing VLSI for the last few years. Different pieces have gone through have gained different levels of maturity, produced different amounts of silicon, and some are quite new, and I'm happy to explore and discuss them with the group here in Q&A.